Mm. There we go. Makes it a little bit bigger. So the first part of chapter 5, what we've been talking about is, I guess, first two-thirds, close to, is the memory hierarchy uh, expressed through the idea of having these layers of cache, which sit in between the CPU and the main memory. And we've just sort of said, well, the main memory's there, and it is where the program is loaded from secondary storage, right? Uh, and that's the current modern sort of layout of how it works. So, in a modern operating system and in a modern computer, we don't run just one program at a time, right? And not only that, but we also have multiple cores. And so we would like to be able to run multiple programs. And therefore, we need to hold those programs as long as possible in main memory, right? In RAM, so that we can run the programs, right? And so they'll all be residing in RAM, and but only a small handful will be actually executing in the CPU, right? Because the CPU is typically only running one or two programs at a time. Uh, but what happens is, since the CPU has billions of cycles, it can switch rapidly between programs, run them for a while, and then switch to a new program, and so forth. And it can also handle interrupts, so it can handle input from the network and the keyboard and the mouse and wherever else it may come. So, what happens though if, like, for example, 40 years ago, we had less memory and you wrote a really large program, right? Then what you would have had to do is, if you wrote a program so large that it didn't fit in memory, you would have to, the programmer yourself, the operating system and the hardware didn't support this, you would have to break up your program into chunks that would fit in memory and had both the instructions and the data that you needed for those instructions, and you would execute that, and then you would switch it back out again. This segmented model was difficult to program. And so, what they looked for is a way that we could instead view memory as a resource that can be managed outside of the knowledge that it's physically constrained, right? So we've got virtual memory. Um, and so instead of having our segmented program, and I'm having to rotate segments in and out as I'm moving through the program code because all of the program code won't fit in memory, what I'll do is simply pretend that I do have enough memory. I can just fit the entire program in virtual memory, right? But when I lay that virtual memory into the physical memory, not all of it will fit. So the pieces that don't fit will be put in secondary storage. And so then secondary storage will end up being another layer in our memory hierarchy. And effectively, then we can treat our RAM as a cache to secondary storage. This will be kind of odd because what we'll really have two copies of our program. We'll have the original copy of our program stored away in the file system, but then we will try to load our program into main memory. It won't fit. So we'll put the parts of the program that can fit in main memory. Meanwhile, the program code that has had data that's been updated because it's been running previously is then uh, put in a temporary location on secondary storage. right? And this is sometimes called a swap file, and because then we can swap parts of the program in and out as we go through. Furthermore, if I now have this large virtual space that exceeds the physical memory, I can also just map all of the programs that I'm running on my computer into this virtual space. And I can make sure using the operating system support this and the hardware that each program has its own address space independent of everybody else. And therefore, no program can act on another. So this maintains security in the system and it protects us against malware or viruses. All of this will be seamless to the programmer so that the programmer doesn't have to do all of the segmented memory management that they had to do before. And they, you just write your program, you compile your executable, and then you pass it off to the operating system and the CPU to manage all of this virtual memory. Right. And so, because this was devised by a different group of people than the ones who did like the cache, um, some of the names got changed in translation, right? So in virtual memory, we don't call it a block, we call it a page, and we don't call it a miss, we call it a page fault, right? The page is faulted because it's not available for our use. So the gray circular disk is secondary storage, whether it be an SSD, a hard drive, it's not RAM, right? RAM is then on the right. The physical addresses is our available RAM. And then our virtual address space is larger than our physical address space. And and if we're filled it all up, what doesn't fit in physical space can be swapped out, therefore a swap file, to a swap file in the secondary storage. So this is going to be additional storage space you need on your secondary storage in addition to what you're storing your original programs and data content and everything. 4K is the typical page size, so that's considerably larger, and we'll get into why that is than blocks tend to be, right? 4K, 4,000 elements. And that's been remarkably, I sometimes see reference to slightly larger, like 8K or 16K. But when I did my assembly programming course back in my undergrad program in the 80s, we were using 4K pages on the IBM mainframe. So I remember that from back in the day. So that was 40 years ago, right? And so some of this hasn't changed. So we'll have our virtual address space and our physical address space, our physical RAM, our secondary storage, and our virtual representation. Everybody got that in mind? No questions? Okay, now the consequence of this setup is that when I need to reach a page and it's not in physical RAM, it's been swapped out, that the fetch from secondary storage is millions of clock cycles. Therefore, that's so slow that we'll let the operating system do that. So we're saved having to put in some really expensive hardware to manage all this simply because it's so slow. There's enough time that we can ask the operating system. So the operating system will take part of this load. And it will manage the fetching and some of the other aspects of our virtual memory. Because placement scheme to get rid of or to find which block, or no, not block, sorry, which page we wish to replace when we bring it in. Because obviously, at the point that we're starting to do page faults, we will have filled physical memory. So to manage all of this, we need some sort of indexing scheme, right? We need to find the address of the page we're looking for. And so what we'll do is we'll have a page table. And so the page table, we index in through the virtual page number, which we found up here from our virtual address and our page offset for the particular page we're interested in. And then the page table tells us where it is in physical memory. If it's a hit, then it'll return and it'll give us all the other status information, which we'll delve into about what else we're going to track for that page. If it's not present, then it's in the swap file and secondary storage, and the page table entry will reference that instead. So what we'll start with is a virtual address. And here he's showing a 32-bit addressing scheme. But for example, the ARM architecture supports an up to 48-bit addressing scheme, which is a lot of bytes. Whereas once we translate the virtual address into the page table, that will then match up. And what we see here is we're using a direct indexing. So we're not using like sets or dividing it up like was a tag and the lower order bits. We're just, all the bits are being used for, all the address bits are being used for indexing. The only lower order bits that aren't being used for indexing are instead, of course, telling us that inside of that page, where is it that we actually want the data from? And so that's our page offset, right? 12 bits is 4K, right? Because 2 to the 10 gives me 1,000, 11 gives me 2,000, 12 gives me 4,000. So this tells me where I need the data from, but this tells me the page I'm looking for. And then the valid bit will, of course, tell us whether that address is going to map to the swap file on secondary storage or to the actual physical address down here. And a visual representation of that is sort of right here. Another nice feature about this is the pages don't necessarily need to be contiguous. So I can load my program, and as it needs more space, it can grow, and I can just allocate it more pages. Because remember, a program will have the ability to allocate storage from two different locations, from sort of the top of its address space, typically was the stack, and from somewhere else in the address space with the dynamic storage, or basically the heap, right? And so instead of just blocking out and not really using large chunks of physical memory, we can just allocate pages, which will be our stack, our dynamic memory, the segments of our code, and our static data, and all of those will be mapped into our pages. Right, and then a 0 for the pages that are here, and a 1 for the pages that are up there. So replacement wise, um, there's enough pages that we really can't track individual pages, but we would like to get rid of the least recently used page. And therefore, what we'll do is adopt a compromise. What we'll do is we'll use a reference bit. And whenever we touch a page, right, read or write to a page, we will set the reference bit to say we access the page. And then after a period of time, there will be lots of pages accessed. There'll be lots of reference bits set. And then at some predetermined time period, the OS will just go through and wipe those all out. And then we'll start accessing pages again and marking it. But the pages we don't access in the next time period will still be zero. And even older pages will also be zero. And so those are pages that we can choose from, right? So something not recently accessed. On top of this, when we write to pages, it's not practical to build this large a buffer because we're writing quite a bit of data because we're writing blocks to and from pages and not just individual bytes. So write through is impractical, and instead we will mark the pages as dirty with a dirty bit, right? And then only once we get rid of the page will we write it back. Now, what wasn't referenced here is where the page table is, right? So the page table can be quite big, and I therefore need to store it somewhere. And a good place to store it is just carve out a chunk of physical memory. So physically, this page table is somewhere in physical memory. That does mean that when I fault or well, let's see, first of all, I miss from the cache and eventually reach to main memory, I'm going to do two lookups in the memory because I'm going to need to first look at the page table to see if it's in memory or not, and then get it from memory, right? So that can have an impact on our performance, and we would like to speed that up. So what we'll use is what's called a translation look aside buffer. I guess because it's a buffer and we're going to translate the address and we're going to look over the buffer and see if it's there instead of looking in the page table like we would ordinarily do. And what we're hoping is it's over there in the TLB and then we can go from there. But so the TLB is a cache of the recently accessed page table entries that is stored inside the CPU, typically around the speed performance of the second level cache, right? And in fact, this 10 to 100 cycles for misses to it and 0.01% to 1% miss rate is typical of an L2 cache. And we're going to make it very fast so we don't slow down the CPU. And the number of entries will be very small. It says here 16 to 512, right? Let me show you what this kind of looks like physically. Let me see. So now the TLB will be sitting in the CPU as a cache. The page table will be physically sitting in physical memory. When I ask from a load or store, right, or I'm fetching an instruction, we'll go through the level 1 cache. Oops, it's not there. We'll go to the level 2 cache. Not there. So then we will bring it to the TLB. We're really hoping it's there. If it is, and it's valid, and it's not been, and the reference bit is for when we remove it. So we're not worrying about that right now. And we pull it out and do our handle our miss. If we don't find it in the TLB, then we will have to search further into the page table entry, which will then go to the operating system and the software to sort through and see if I can find all of this in the page table. And then we're still hoping, of course, that it is a valid bit and we'll find it in physical memory and be able to fulfill our request in just a few hundred clock cycles. All right, I think I remember from Monday, the example is 400 clock cycles for the example that he gave. If we're truly unfortunate, then we're in the page table and it's not valid and it's been swapped out to the swap file. Then we're waiting a few million cycles. So probably we might as well go run some other program while we're waiting for this program to get up to speed. So as I said, the page table's in physical memory. And I remembered back in the million transistor link from IEEE for the Intel i860. So this is a RISC chip, and it was it was the first million transistor CPU, but it was very quickly followed by the 46 a few months later. And so we see an instruction cache, a data cache in the bottom left and bottom right. But then if we take a look over at the top left, we see TLB control, TLB storage. CAM is a type of fast addressable memory. So what they're using is when they ask for something, it quickly tells them if it's there or not. And so they have 64 entries in their translation look-aside buffer. And then this would go outside to the RAM to get to the page tables or then to the actual page and bring it back in. And if we look at the silicon version of it, it's right here too. So a very regular appearance because it's simply a cache of addresses to be referenced as we're accessing data. So the painful part is if we get misses. The first miss is, of course, that it's not in the TLB, but it's still in the page table. So we'll have to do a memory access to RAM. And either do this with some hardware because we're still dealing in memory, or maybe a very fast piece of software as part of, or a mix or combination of the two in order to get this going. But if when we look in the page table, it's been swapped out, then that's a page fault. Then we'll just simply put it in the operating system's hand because it's now in millions of clock cycles or thousands of clock cycles if we're looking at an SSD. Let's see, and I think this is sort of more of a reiteration. If the page is present, and one thing we can do is if we do access a page table entry, we can realize that, hey, maybe we are going to keep accessing that for a while. So let's promote it up to the TLB, right? And so if it missed from the TLB, we'll get rid of something from the TLB and promote our new place that we're accessing in a TLB and restart our instruction, right? And the RISC architecture was designed from all this from the get-go because virtual memory had been around long before the 80s. And so restarting instructions very fast because remember the write phase of the instruction is not till the end. So I can always interrupt the instruction or drop it and wait to restart it at a later time. Let's see if there's anything else. For the page fault, we are now accessing secondary storage. So we've pulled the address out, we've located the page. We go back to our, what's the bit name? The reference bit, and ask it, find one that's not set to 0 to replace. If it's dirty, we got to write it out first, and then read the page into memory, update the page table entry, and again, tell the CPU we're ready for business and we can move forward. Now, there's a whole couple of pages in the textbook about this physical address versus this virtual address. At what point in time do I move from using the virtual address to reference everything to using the physical address? The complication can be that I could have different virtual addresses that end up getting mapped across to the same shared physical location, depending on timing, right, as things go through. So it might be better to just maintain the virtual address as far as possible until you finally have to translate it into the physical address. That's where the translate in T comes into play, right? And so let's see. We take the virtual address, we compare and find it in the TLB. The TLB in this model right here on this page has the physical page as a map to the virtual page. And then we pass the physical page, or at this point, we have the physical page, and so we can go to the cache and see if it's there. And so in this particular model, the cache and when we're accessing the RAM are physical addresses, and when we're accessing it inside the CPU at the TLB level, we're dealing with the virtual address. And we break it out until we get our data and we come back. Additional complications on this can be if you have two different programs who want to share data between each other, which is a possibility and can be set. And so that can throw a wrench into this entire process to manage all of this. To be honest, at this point in time, we have gigabytes of memory. So if I go to my MacBook and look at my memory or bring up my activity monitor, and let me move it around so I can get to it. All right. Let me bring that up instead. So it's all right. So if I look at my activity monitor, it says I'm running, wow, 700 programs and 3,000 threads on here. And it's basically about 80% idle. But if I, since we're in chapter 5, switch over to memory, I have 16 gigabytes of physical memory. I'm using 12 gigabytes of that, 7 devoted to applications, 2 to some other reference. Some of it's compressed. I've cached 3 gigabytes, and swapped use is insignificant, right? So the memory pressure, or how much that I need, is way below what I physically have available. And so I don't need to use a swap. So in many of the modern systems, until you really stress the machine with lots of large applications consuming lots of data, the swap is essentially just not used at all. Right? And in this case, if I look at my memory utilization, Finder, equivalent to Windows Explorer, is taking up a gigabyte with 8 threads. And Google Chrome is remarkably way down low, only about 100 megabytes down here. And then lots of other stuff along the way. So if we're not using it for additional storage or additional memory capability, then what is it good for at this point in time? If you look at what the author spends a lot more time on in the chapter than he does in the slides, he talks about virtual machines, right? So virtual memory is a very good way to help support virtual machines, make sure they don't conflict with each other. And virtual machines tend to be very large. And so that might be a place where we could potentially start swapping. But basically, memory protection is the overriding mode for our virtual memory here, because when we load up the application, we'll be doing that by double clicking in the Explorer, which is part of the operating system. So the operating system will come up. The operating system will manage all of the virtual memory. It'll do it in its privilege mode, sometimes called kernel mode, and only the operating system can touch the page tables and everything else, and anything that the programs want will be handled through the operating system, either through the interrupt mechanism or through some other specialized hardware operating system OS combination in order to protect your program from other programs. So that's virtual memory, I'm pretty sure. Yep. Any questions about the virtual memory system? All modern operating systems have it, right? I do remember back in the day, um, when I had DOS, having to reboot my computer from doing office work to doing gaming. I would have to reboot the computer to set up the memory differently for the game to run. And the game would effectively replace the operating system. So it'd have unfettered access to all the resources to have the best performance. Nowadays, that's no longer true. The game is still running underneath the operating system, like on a console such as an Xbox or PlayStation, because of course the operating system is also managing the network card and your ability to take snapshots of the game and exchange messages and do the voice and all the other components that aren't necessarily something to be managed by the game itself, as it focuses on the gameplay and the graphics. So near the end of the slides, what he's done is he's reiterated the memory hierarchy stuff. So this is a good place to go take a look for review, right? And so it's a good place to summarize everything we've talked about over the last couple of weeks. So everything is based off of this principle of locality, is actually how I'd more characterize that. But we do this through caching, right? And so we're looking at temporal locality and physical locality. All right. So temporal locality, accessing the same value over and over again, executing a loop over and over again. Spatial locality, accessing the next element in an array, accessing the next instruction in a block. So nowadays we got our level 1 cache, or we got our registers, our level 1 cache will go as a level 2 cache, possibly a level 3 cache, RAM, and then secondary storage for our swap. So quite a few levels. And at each level, we need to find room to put our data, our instructions. We need to then, after we've put it there, don't forget where we left it. And so we have to come back and be able to find it to use it as we work our way through the block. Once we're done with it, and we want to really fully 100% utilize our memory system, especially our cache, because that's the fastest component of our memory system. So eventually we're going to need to do a replacement. And if we have stores and a program updates its data, then we're going to have some sort of write policy. So we started off with direct mapping using just simply modulo or simple math to figure out where we're going to place things. It gives us one choice. The contrast is fully associative, which is the model that virtual memory uses. The associativity maps directly to being able to reduce the miss rate, right? Because I'm very quickly going to exceed the block, so I want more blocks. And so being able to find them and put them together, the more flexibility I have, the better that would be. But there's a point of diminishing returns, especially in a limited space. The cost of the fully associative scheme and some of the in-way set associatives is the number of comparisons that are being done. And in cache, we want to do those comparisons in hardware. So that makes the cost dramatically more expensive. So typically, if I have 1,000 entries, I'm not going to make it 1,000-way fully associative. I'm not going to even make it like 512 or 256 or 64. It's most likely going to be something like 2, 4, or 8 in the level of associativity. So significantly smaller fraction. But even that small fraction is still better than direct mapping, significantly enough that typically only embedded or lower end systems nowadays still use direct mapping. Of course, the access time delays for virtual memory allows fully associativity to be feasible. Plus, we'll do the searching in software with some hardware support. In that case, the pages are large enough that we're going to have a really low miss rate, but we want to make it even lower because the cost of replacing a page is so high. So once we're filled up our cache, if it's 2 or 4-way, we can do least recently used. Above that, fully associative or other levels of associativity, we'll just use random. We can implement that relatively quickly in hardware. And tests have shown that it performs about the same. For virtual memory, we still don't have the storage space or the performance to try to really track thousands of pages. So we'll use that reference bit and simply clear the reference bit after some set time period so that we get some sort of approximation of least recently used. And then just as a reminder, we've got our write through and our write back. Write through, something that can be done in the cache. I'll just simply write through the upper and lower levels of the cache. Therefore, I know everything is synchronized or consistent all the way through, and I can easily dispose of blocks when I need to replace them. But I don't want to be held up by writing to the slower levels of the cache, so I'll have a write buffer to make that all work. Alternatively, I'll use a write back scheme. I only update the fast layer, which is the upper layer, and then simply mark that layer as dirty, and then only write it to the lower layers when I remove the block for replacement. Obviously, you've got to keep track of the dirty bit, and you do a little bit more work whenever you remove a block because then you have to copy its contents to the write buffer and let that happen as I then replace the block. With millions of clock cycles on a spinning hard drive or thousands of clock cycles on an SSD, write back is the only feasible choice as virtual memory. And then the textbook characterizes this as a 3 C's. I don't know why he couldn't simply put that up top, the 3 C's. But we got compulsory, capacity, and conflict misses, right? The compulsory is the first time I touch a block, it's not there. So that's a compulsory. Another name for that, cold start. And we can mitigate that with trying to like load things ahead of time as we're accessing the program for the first time. Go ahead and initialize some things to make things run faster. You can also see kind of an interesting approach to this. For example, with things like Microsoft Office will preload some of its software at startup time. So components that are shared between the different Office parts software, they'll preload some of the initialization software so that therefore when you try to start Microsoft Word or PowerPoint, it runs quicker, or it looks like it starts quicker because it actually already started. You just didn't know about it. Of course, we have a finite cache size, so that's where capacity misses come into place. And then conflict or collision misses in a non-fully associative scheme that's got a limit finite space. We're competing on our blocks. And that is something else we have to handle. All right, so those are the 3 ways to think about where misses come from. And then on the next slide, we have a trade-off of how we might resolve some of those, right? So I already mentioned for the compulsory misses, they might do something like preload the block, right? As the program comes into play, it's going to be available for run. Another way that we can do it is increase the block size, right? So if I'm accessing instructions in sequence, if I have a larger block, then I'm going to access more instructions before I have to replace that block or move to the next block and look to make sure it's there. The downside is if I try to have more larger blocks, my cache is bigger and potentially slower. And too large a block might mean that I only want part of the data on the block and the rest of the block is just taking up space. So that's our pollution. So then if we look at our capacity misses, well, just make the cache bigger. But again, that might increase the access time. So what we find is the level 1 cache has been pretty fixed in size, but the level 2 cache has been growing in size as we move through time. And again, conflict misses, increase associativity, increase access time, increase complexity in order to make all of those happen. All right, so like I showed you the cache for this machine, and this laptop is running an M1 chip. And so if I take a look, right, we have 192 instruction, 128 kilobytes of data cache for the performance cores, 128 for the and 64 for the efficiency cores. right? I believe it has 4 performance and 4 efficiency cores. So each of the cores has their own level 1 cache. Then the performance cores and efficiency cores are split apart, and they each share a level 2 cache, but it's different from, for example, the efficiency core's level 2 cache. And then there's a system or level 3 cache that can also be shared by the GPU unit. And on the low end chip, it's 8 megabytes. As you go up to the Ultra, then you get to 96 megabytes for the level 3 cache. Because, of course, you need to serve a lot more CPUs. But as you add more CPUs, they each include their own level 1 cache, and each cluster comes with its own level 2 cache, which there is in megabytes versus kilobytes. So 1,000-fold bigger to go from level 1 to level 2. So we'll stop here. The next slide is talking about the controller for the cache system. So we'll do that and the rest of the slides on Monday. So have a good weekend and get into chapter 4 homework, and I'll see you next Monday.
Don't ask me, I'll never tell. I look to use as it felt, and now you're in my way. I trade my soul for a wish, pennies and dimes for a kiss. I wasn't looking for this, but now you're in my way. You're still.
You're behind. Skin was showing. Hot night, wind was blowing.
You're behind. Hey, I just met you,
You're behind now.
and this is crazy. But here's my number, so.
Engage or evade the enemy as you move toward your exit. Thankfully, your shell is equipped with powerful
I got you.
Yeah, I got TJ.
Holy.
I don't.
How are you like dripped out like that?
What?
Who?
You're looking fucking damn good.
Who?
We all look the same.
Oh no, never mind, Mike. Never mind. You were on the other character, I think. You were on Void.
Ecosystem.
Who's the guy with the shield?
This is gonna be fun.
What
That's called Newcastle.
Everyone get your quest. Get your quest.
Where's quest in this shit?
Yeah, get your
That's
contract.
called Newcastle.
Did we go to Sayak?
We got a funny guy.
Yeah, what map? Do you guys want to do the new
Hold
map or
on,
do you want to do Dire
activate.
Marsh?
We got a funny
Let's do
guy.
Dire Marsh. Oh, yeah. Wait, they're both selected. Okay.
I'm gonna be making jokes like that.
Oh, wait.
all day, you heard me?
I load out. You guys good loadout wise?
I don't fucking know. Sure.
Load
Make
out.
sure you go to your menu and fucking give ammo and shields and meds. And
Yeah, I got 100 bullets. I'm good. Get it. Let's get in there. Let's fucking ride.
No,
Let's
no,
ride.
Bring a little more. Bring a little
Let's
more.
ride. Ready?
I'm fine. The mechanics kit. I need to get rid of my pistol though. Hold on. How do I get rid of this pistol? Vault the pistol. All right, we're good. We got an SMG. Nade.
Ready it
We're
up, bro.
fine.
All right, fine. I'll bring
Going
more
up.
bullets. I'll bring more bullets. 300.
I have 400 bullets. We're
Okay.
good.
Let's ride.
Oh shit! You're not bringing a second gun? All right.
Fuck
Guess
no.
I don't know. I might need a backup.
Bro, what was this, Call of Duty? What do you mean?
What do you mean? That you might not kill someone with the first mag, and what if you just fucking get run down?
Ready up. Let's ride.
I turned off the reflex.
Oh.
So that might be it.
Maybe,
I'll see if
maybe.
reflex is
On plus
causing it.
boost. Yeah,
Reflex is
that's
buggy
what I was saying.
sometimes.
Off completely.
Oh, off? Like
Yeah,
just
I'm
off?
seeing if it works. I'm doing the testing.
Okay.
Let's get fucking get crazy.
I like the menu music. Just the music in general in the game's
Yeah,
fucking.
that's
It's
what I'm
hot.
saying.
It's
The
fucking
music is
hot.
like-
It's hot.
Music is the best part so far.
I think the whole art direction in this game is the best. Can't lie.
I am not fully sold yet.
Nope.
Yeah, I'm
I
not
love
fully
the
sold
art.
yet
I
on
love
it.
the
I
art.
need
I
to
can't-
play it more to see if like the art really resonates with me.
Shit's
But
dope.
I also don't care. I just want to shoot stuff, you know? I don't care what
Yeah.
I'm shooting at. I don't care how it looks. Iscuity, thank you for the prime.
Oh!
My
Thanks,
mic sound
boys.
good on Discord,
Wait.
by the way, or no?
Nah, it sounds
Yeah, it
awful.
sounds fine.
No, I'm just kidding.
Oh.
I'm just
Alright.
kidding. I'm just kidding. I'm just kidding. It's a
Alright.
joke. Let us in,
Are we still
bro.
preparing or what? Like,
What's everyone's FPS on this menu?
392.
455. Okay.
400.
wait, I have more FPS than you.
Well, yeah, you
That's
should have a
for
better
the
computer
menu.
now, right?
No,
McNuggets, thank you for the
not
sub, brother.
Than you though. Still a 3080 in my shit.
Oh, we're in.
Are we?
Your gear's at
Can we
risk.
TK?
I don't think so.
What? You can't TK?
No, you can't. You
I don't
can't.
think so.
Chalk it up. Chalk it up.
I think just util maybe, just like most games. Dire Marsh. Is this fucking WoW?
130. We went up.
178.
I lowered all my
182?
graphics and I lost FPS.
Wait, let me turn on
I mean-
reflex real quick.
Background processes engage.
That might be better.
Searching for signs of human life. Survival metrics are unfavorable.
I actually
we
lost
spawn trap
FPS. This is
people?
weird.
I think I lost FPS turning that shit off.
Can we spectate people? Yeah, for sure. What is this fucking? You think this is 2004? Of course we can. I guess we spectated
Do
people
my
back then
room.
too. Hey man.
What's up? You look like Newcastle.
Yeah, I'm playing the boy with the
make that joke
shield.
again.
Listen, I'll be your entry fragger, okay? I'll go in with the shield.
Alright,
you
sound
guys
good.
pop out from the back.
On a ladder.
I don't like the way you run.
Me?
Oh, I didn't even know you could slide. That's hot.
Me? Or you?
Yeah, the way you run is silly.
I mean, I'm kind of a big boy.
I got something. Putty explosive added.
Yeah, this
teams
is
don't
so
cross the
weird. This
fucking
game
map.
should
The fuck?
run better for sure. We were absolutely lied to. Everyone that said that this game ran 200 plus FPS
we lied.
is
They were
absolutely
They lied.
every
They
single
lied.
content
There's a
creator
bad
that said
guy.
that in the test is a liar,
Yeah.
lying through their
It is
teeth.
not running.
Why are they lying?
I don't know.
That guy's low there.
Hey, magnetism. Oh, that shit feels nice. Dude, I'm so down. It's the day and age. It's the day and
Wait,
age of
dude,
mouse and
it's so
keyboard.
bad.
It's the day and age of mouse and keyboard getting freaking aimbot. You know what I'm saying? It's. Oh, look at that aimbot.
That is
Yes.
nice. That is
Yes.
nice.
Oh my god, I'm aimbotting. I'm actually aimbotting.
Oh my
losing
god,
it.
it's incredible.
I'm fucking
Bro,
aimbotting.
we have no fucking space.
Oh my god, I'm fucking aimbotting.
We deserve this. We deserve aimbot. We deserve it. This is our moment.
I'm gonna be honest with you, there's no space.
Yeah, we shouldn't have brought so many
Console
bullets,
game.
too. I got a grenade.
I'm gonna turn aim magnetism off, I think. It's just like too...
It's too
I
good. It's too
absolutely
good. I love it. I
It's
love
like
it.
too
Whoa.
good.
I love it. I'm keeping it.
Oh.
This loot is probably ass. Let's go get some real loot. Let's go to,
Apparently the mobs are like free loot. Apparently.
I'm going to field maintenance. So many bullets. Yeah, you definitely don't need to bring more bullets. You could just kill the first set of mobs.
Yeah. The disaster kit. Oh, it's literally just so.
Oh yeah, I gotta use my shield cells, huh?
If I get aimbotted, oh wait, bro, everyone's gonna have aim magnetism on. So I
Yeah,
have to
everybody's
turn
gonna
it
be
on,
aimbotting each other. This is a game of aimbot. No actual aim.
Dude, I actually have to turn it on.
Yeah, you have to have aim magnetism or you will
Or
lose.
else it's just like
Yep.
I'm just at a disadvantage.
Yep, they definitely should rework that. I don't care. I'm fine with giving aim assist to controllers. Just like it's fine.
Holy shit! Is there a key?
Yeah, but how fast are we dying?
Not that fast. There's a door to. I think there's a computer to the right.
I mean, I just took damage. I barely even touched it. Hold on. I gotta heal up.
Oh, yeah, the video reflex feels pretty bad actually. Turn it off. Like, I can explain it. There's some type of like weird lag. Oops.
Yo, that fucking hurt,
Does
bro.
it?
Yeah, don't touch that.
Okay, we don't go in
It
there.
will-
We don't do that. We don't do that. We ignore it. Purple shields. Who the hell is this guy? That guy's gonna have loot. No,
He's Giga.
he's Giga.
Bro, he's so strong. Holy shit, we need
Loot
better
him,
bullets.
loot him, TJ. Loot him.
Detected.
We need AP bullets.
You guys just go kill him. What do you got? What do you got? We had
What was that?
sports
What is it-
equipment for 550.
What does that even mean?
I don't know, just a piece of loot for 550 bucks.
Holding ground.
That is not the button I wanted to press. I need to change my use key. Keep hitting F on everything. It's just my ability.
Can I read my abilities? Is there like a key for it?
F1 maybe?
F1's the
Valorant
classic,
way?
but no. Just use them. Fuck it.
Loadout. Wait, can I? Oh, amplify. You can just in your loadout.
So we're like, they're players.
Well, I have
stomp.
stompies
They're
from D2.
players.
I have a slide and I
No,
have
no, there's
just
something dropping right
movement.
next to us. There's a ship dropping. You see
Oh,
that?
shit. Yeah.
Oh,
Wait.
it's enemies, enemies,
Oh,
enemies.
enemies.
Come on.
Like real med?
That's a. Yeah, that's. Yeah, players.
Oh, yeah.
Wait, who's shooting on the right here? Oh shit! I'm getting naded. Oh shit!
I'm healing.
No, it's not. It's not.
Oh, okay.
All right, where are we going?
Okay, turns out you can't hold nades. I pressed G and it just threw. So just be aware of that. I don't know. There's a bunch of enemies over here. Where I'm at.
Oh my god. I fucking hurt. Oh wait, I'm getting pushed. How do I cancel my heal?
Bro, you guys dying to AI?
They're
Yeah,
purple
honestly,
AI, purple and gold and
Oh,
shit.
they're-
Oh, this is depressing, bro. Alright, now I'm Giga.
think he's really good end of game body too, man.
We'll do it together, man.
Yes, sir.
Especially after the Super Bowl.
If I was you, I would never come out. And they're paying you pretty good to play college football. Why the hell are you coming out?
I mean, I think it's just time for me to go into the next part of my journey.
Does anybody know about this? Is this why you're coming out of Texas? What is
You
this?
got this pulled up, man?
Yeah, I found it.
I should have known that. I should have let my girl
Look at
post
it. What the hell is this?
it.
What is it?
It's some TikTok trend. I don't even have TikTok, so I didn't know what was going on.
I got TikTok, man. I found it.
Do you?
Yeah.
I deleted that crap.
Yeah, just stand up. How do you throw the football? Like, give me 2 or 3 pointers.
I've always had the ability to throw a good ball, and a lot of it's in my wrist. And I think that's how I'm able to get all those different arm angles going. You know, grew up playing baseball, which was big for me, but as long as I get a quick late tap on the ball to speed everything up, and as long as I get that front foot down quick, and I put this right foot down with urgency right here, real quick after I throw the ball, I know it's going to be a good ball.
It's awesome, man.
Yeah, it's all really down here. And as long as, yep.
Okay, so to do that, what are the keys of being a great pocket passer? Tell me.
I mean, number one, having footwork aligned with the route concepts.
And I want to know why you're changing your footwork. I mean, you've been at Sonny Detmer's passing camp when you were in the 3rd grade. I know that.
How do you know that?
I know the Detmers. I know everything. I know everything about quarterbacks, man. I got friends, you know.
That's a throwback, man.
Well, why would you change your feet when you've had this much success? You got a great arm. You got great arm talent. You make exceptional throws. I mean, some of this shit right here, that is as good as
The fundamental difference between accelerator and accelerated computing is accelerated computing is programmable. Accelerators, they are configurable. They're programmable in a very, very specific set of algorithms. For example, an accelerator is like a DVD decoder. That's an accelerator. An Ethernet chip is an accelerator. An Ethernet chip never becomes a DVD decoder, and a DVD decoder never becomes a GPU. And our GPUs, because of CUDA, is both an acceleration platform for many domains of applications, from image processing to particle physics to quantum. You've probably seen that we announced recently some work that we've been doing in quantum. We're doing incredible work in quantum computing as a quantum emulator, all the way to an intelligence emulator. We call it artificial intelligence. And so our platform is programmable. And also because we have the discipline of ensuring our entire installed base of GPUs are CUDA compatible. Every new algorithm that is developed on any of our GPUs will run on all of our GPUs. And that gives the developers reach, while it gives the new developers the capability to solve problems they couldn't solve before. And so simultaneously, we can solve new algorithms like transformers that came along, and multimodality transformers, and new algorithms like SSMs, and all kinds of buzzwords that most people haven't heard about. We have 100% confidence they all work on CUDA. We have 100% confidence they all work on NVIDIA GPUs. And once they work on NVIDIA GPUs, because our installed base is so large, millions of GPUs in the cloud, we're in every single data center everywhere, we can therefore take that innovation and benefit everybody. Maybe the performance is not as fast as our latest generation, but it works on everybody's. That is just a wonderful benefit. And you were asking about inference. The goal of inference is application reach. The goal of inference is application reach. It's no different than the goal of writing an application for a mobile device is application reach. You prefer a phone with the largest installed base. It is fundamentally the reason why Apple is so successful. In our case, inference, anybody who's developing an application to run inference is going to prefer NVIDIA first. And the reason for that is because the CUDA install base is so large. It is the only acceleration platform that has a giant install base. It is in every single cloud. It is growing incredibly fast. And it's available on-prem or in the cloud. It's available all the way out to the edge for robotic systems. And so this architecture, being so pervasive, and because we have the discipline of protecting it and maintaining it for 30 years, this architecture is now literally everywhere. And if you are somebody who's developing an application for inference, targeting NVIDIA gives you the largest possible reach.
CUDA, a parallel computing platform that allows you to use your GPU for more than just playing video games. Compute Unified Device Architecture was developed by NVIDIA in 2007 based on the prior work of Ian Buck and John Nichols. Since then, And CUDA has revolutionized the world by allowing humans to compute large blocks of data in parallel, which has unlocked the true potential of the deep neural networks behind artificial intelligence. The graphics processing unit, or GPU, is historically used for what the name implies, to compute graphics. When you play a game in 1080p at 60 FPS, you've got over 2 million pixels on the screen that may need to be recalculated after every frame, which requires hardware that can do a lot of matrix multiplication and vector transformations in parallel. And I mean a lot. Modern GPUs are measured in teraflops, or how many trillions of floating point operations can it handle per second. Unlike modern CPUs like the Intel i9, which has 24 cores, a modern GPU like the RTX 4090 has over 16,000 cores. A CPU is designed to be versatile, while a GPU is designed to go really fast in parallel. CUDA allows developers to tap into the GPU's power, and data scientists all around the world are using it at this very moment, trying to train the most powerful machine learning models. It works like this. You write a function called a CUDA kernel that runs on the GPU. You then copy some data from your main RAM over to the GPU's memory, then the CPU will tell the GPU to execute that function or kernel in parallel. The code is executed in a block, which itself organizes threads into a multi-dimensional grid. Then the final result from the GPU is copied back to the main memory. A piece of cake. Let's go ahead and build a CUDA application right now. First, you'll need an NVIDIA GPU, then install the CUDA toolkit. CUDA includes device drivers, a runtime, compilers, and dev tools, but the actual code is most often written in C++, as I'm doing here in Visual Studio. First, we use the global specifier to define a function or CUDA kernel that runs on the actual GPU. This function adds two vectors or arrays together. It takes pointer arguments A and B, which are the two vectors to be added together, and pointer C for the result. C equals A plus B, but because hypothetically we're doing billions of operations in parallel, we need to calculate the global index of the thread in the block that we're working on. From there, we can use managed, which tells CUDA this data can be accessed from both the host CPU and the device GPU, without the need to manually copy data between them. And now we can write a main function for the CPU that runs the CUDA kernel. We use a for loop to initialize our arrays with data. Then from there, we pass this data to the add function to run it on the GPU. But you might be wondering what these weird triple brackets are. They allow us to configure the CUDA kernel launch to control how many blocks and how many threads per block are used to run this code in parallel. And that's crucial for optimizing multidimensional data structures like tensors used in deep learning. From there, CUDA device synchronize will pause the execution of this code and wait for it to complete on the GPU. When it finishes and copies the data back to the host machine, we can then use the result and print it to the standard output. Now, let's execute this code with a CUDA compiler by clicking the play button. Congratulations, you just ran 256 threads in parallel on your GPU. But if you want to go beyond, NVIDIA's GTC conference is coming up in a few weeks. It's free to attend virtually, featuring talks about building massive parallel systems with CUDA. Thanks for watching, and I will see you in the next one.
About 20 years ago, NVIDIA had these GPUs for just rendering lots of pixels. They still have them. And a guy called Ian Buck, for his PhD, said, what if we use this for fluid mechanics? And so his PhD was built on turning graphics processing into normal computing. And he came to NVIDIA and built CUDA. So I was one of the, one of the first dozen people in CUDA, I think. So when I got there, it was barely programmable, and we sort of built bits and pieces as we went. But really, so what it tries to do is, in any program, you've got bits of your program that are normal, open files, fetch an API from the internet,